I would prefer also choosing one that asks us to determine the equation of the tangent line, because that's why we're doing this, one reason. But it's up to you if you'd like to. This is called implicit differentiation. We can use and determine those, and then later on choose a problem from any preference.
Number 8.
Which one?
Number 8.
Number 8. Very good. So let's take a look at number 8. On to 15. Number 8. It's 2x to the third plus x squared y minus xy cubed equals 2. And then I would like to look at problem 12 because it has cosine in it. So after that, 12. Any questions so far?
Now this won't require any of the product rule.
It requires the product rule here. There are two functions. This is function 1, function 2. Function 1, function 2. This one does not. Good. So no one can solve this for y. Don't even try. So let's find an expression for dy over dx. Since we are asked to find dy over dx, we are implicitly told, listen, y is not a variable, of course, it's a function of x. Okay, so that's what we're asked to find. Ready? Can anyone dictate the left-hand side? 6x squared plus the first function prime, 2xy, very good, plus x squared times dy over dx minus. Be very careful now. I'd rather you have parentheses in order not to forget to distribute the negative sign. Or if you keep that in mind that you have to distribute the negative sign, that's fine too. So the first function prime is 1 times y cubed plus x times bring down the power 3 times y squared times dy over dx equals 2 prime, which is perfect. Let's distribute now and clean it up a little bit. 6x squared plus 2xy plus x squared dy over dx minus y cubed minus 3xy squared dy over dx equals 0. I see again that dy over dx is present in two terms. I will keep these two terms on the left and I will move the other three terms to the right. So this will go to the other side. This will go, and this will go. Yes?
For the minus xy to the 3, would the x just turn to 1 and you just leave y to the third?
Which part are we looking at?
At the second step, when we were
You
with
mean,
the
here?
parentheses,
In this one?
no. Oh, down. Yeah, right there.
So the first
that's
function
when-
prime is 1 times the second function plus the first function times the second function prime, which is 3
okay.
y squared times the inner function prime.
Gotcha. Yeah.
So remember, each product turns into a sum of two terms.
Right.
Each product turns into a sum of two terms.
Gotcha.
Everything okay? Other questions here? Okay, so then I will factor out dy over dx. So x squared minus 3xy squared dy over dx. And then I move y cubed to the other side. I move negative 6x squared and I move negative 2xy. And now I'm ready to solve for dy over dx. Are we ready? So y cubed minus 6x squared minus 2xy over x squared minus 3x y squared. Is this okay? Were you able to keep up? So this is implicit differentiation. Extremely powerful tool. Okay, I said let's also look at number 12, same page. Cosine applied to xy equals 1 plus sine y. Same question. We're asked to find dy over dx. This is not a friendly situation. Why? First of all, because I have a trig function, and inside that trig function there is a product. So we want again dy over dx. So let's differentiate the left-hand side and differentiate the right-hand side. I'm ready when you are. Very good. Cosine prime is negative sine of xy times the inner function prime, which has to be a sum because it's a product. It has to be a sum of two terms because it comes from a differentiating of a product. So the first function prime is 1. So times the second function plus the first function times the second function prime. Very good. Equal symbol. And now 1 prime we know. I have to differentiate sine, and inside sine there is this function y. So I have to differentiate sine first. And I get cosine y. And now I have to differentiate the inner function, dy over dx. Would you agree? Questions? Okay, let's take a look now. This is the variable we are after, but it's inside a set of parentheses or brackets. So first I have to distribute this factor here and then move terms around. I have to eliminate the brackets first. So this times this will be negative y sine xy, and this times this will be negative x sine xy dy over dx equals cosine y dy over dx. Only now I will move this term to the other side. So I'll move the second term to next to cosine y dy over dx because they both have dy over dx, and I leave alone the negative y sine xy. Questions? Is this okay, everyone? Are you able to follow, please? Yes? Okay. So then we have negative y sine xy equals x sine xy plus cosine y. I did 2 steps in one. What did I do? I moved that term to the right-hand side, and at the same time, I factored out dy over dx. Because now we have it ready to write the final form of dy over dx. What do we have at the top? Right here. And this is on the denominator. There is no need for parentheses around the denominator. This is it. Okay. There are 6 trig functions and 6 inverse trig functions. We know the derivatives of all 6 trig functions. I'm only asking you to remember 3 of the inverse trig functions, just 3. So I would like us to remember arc sine prime, arc cosine prime, and arc tangent prime. Of course, there exist arc cotangent, arc cosecant, and arc cosecant and arc secant. I only want these 3 because they are the most useful ones and widely used. 1 over the square root of 1 minus x squared. Arc cosine prime, same thing with minus in front. And arc tangent, 1 over 1 plus x squared. So the first 2, when we differentiate the inverse function of sine, it's 1 over the square root of 1 minus x squared. When we differentiate the inverse of cosine, it's negative 1 over 1 minus x squared. And arc tangent prime is 1 over 1 plus x squared. Of course, if we have a function inside any of these, what would you say? Arc sine of a function of x prime. What will the answer be? 1 over the square root of 1 minus the function squared, but times what if I have arctangent of a function? What will that be? That's it. Always remember, for anything else that other than plain x, you have to multiply by the function prime. Okay, let's apply this to a couple of examples. See how this works. Okay, so let's look at 56. F of theta equals arc sine of the square root of sine theta. Let's first of all look at this function and decide how many functions are in there. The outer function is arc sine. The next further is square root. And the last one, the innermost one, is sine x or sine theta. Perfect. So let's differentiate. F prime of theta. First, we have to differentiate arc sine of whatever it is. What is the answer? 1 over the square root of 1 minus this quantity squared. Can anyone square this quantity? Very good. Times. Now it's of this prime. But I haven't gotten to sine x. I have to differentiate the square root now. What will that be when I differentiate the square root of a function? 2 the square root of sine theta. But now times cosine theta. You don't have to do anything else. You can leave it alone. Any questions? What about 54? Any questions for me on 216? 216. Any questions? 54 is y equals tangent inverse of x minus the square root of 1 plus x squared. This is the same function with arc tangent. Do not assume that this is a negative power, that you bring it down, and no. Be very careful. Tangent raised to negative 1 is the inverse function of tangent. This is not 1 over tangent. So we have two notations for tangent inverse x is the same with arc tangent x. This is not a power. This is simply the inverse function of tangent. Okay, so we want to find y prime. Since the function is given directly, I would not use the notation dy over dx. Sometimes we will, however. But here I would not. There is no need. The function is given directly, so y prime is fine. Okay, so can anyone tell us what to write? So we have, first of all, arctangent. Then we have the inner function that is a difference of two functions. So first I have to differentiate arctangent. What do I get?
1 over 1 plus x1.
Yes, so it's 1 over 1 plus this whole thing squared. X minus the square root of 1 plus x squared squared times. Times what? 1 minus, and now I have to differentiate this. It's again the square root of a function prime. What do we get? 2 the square root of that function times 2x. It can be further simplified, but I'm fine with it as is. So I'm just going to write y prime as, I'm going to multiply this by the square root of 1 plus x squared because the least common denominator is this. So the square root of 1 plus x squared and minus x, everything divided by, I'll put this in front, the square root of 1 plus x squared, and I copy this. Let me use brackets now. 1 plus x minus the square root of 1 plus x squared squared. And yes, it can be simplified. I may be able to rationalize the numerator, but it's okay. It's fine. I'm happy with this answer so far. Any questions? Yes, please, Eddie?
So you're always working from the
Outer to the inner. Yes. Yes. When I decompose a function, I start with the inner. I'm asking myself, what function do I apply first? The inner. If I want to evaluate. If I want to evaluate this function, I cannot start with the outer. I have to evaluate the inner function for x equals 1, let's say. Right? And then I finish with the outer function. But when I differentiate, I have to start with the outer function and work my way into the inner. Slowly. Like we had that example. I think that was maybe the best example to explain that. This one. So first we had to take care of this power. That was the last thing I would have done if you would have said to me, evaluate this function for pi over 2. This would have been the very last thing I would have done. The first thing I would have done, I would have put sine in here, so pi over 2, and then I would have squared it, and then I would have applied e to that, and then I will get a number, and then I will apply sine to it, and then when I'm done, I'll square when I evaluate. But when I differentiate, I have to start from the outermost. I differentiate this, then I differentiate this, then I differentiate this, then I differentiate this, and then I differentiate this, and then the power, and then sine. Is that better? It will get better with practice. Any questions on, I only want you to remember these. I will not test you on anything that is not basic. That's basic. That's the 3 functions. If I put anything else, it will be the formula will be given to you, but I'm not interested. You can always look up a formula. As long as you know the basics, you're fine. Any questions for me here? Can we move on? Okay, let's talk about log. We haven't talked about log function in terms of its derivatives. So 3.6, derivatives of log functions, logarithmic functions. So f of x equals natural log x. We graphed it a few times because it's such an important function. F prime of x is 1 over x. What if I have a function that is natural log of a function? How do I differentiate this? It's 1 over the function times, of course, the function prime. what is a mechanism that is extremely important here is when I want to differentiate a function, let's say sine x raised to tangent x. We'll have examples with log in a minute. I just want to emphasize this for a second. This is a major topic, by the way. I haven't told you what it is yet. I will in a second. So what will you do here to differentiate a function raised to another function? You will bring down tangent and subtract one from tangent and differentiate sine. Not possible. We do not have a formula for a function raised to a function. A function raised to another function g, no formula or rule. No differentiation rule. Nothing that you've seen before is applicable here. Don't ever try. Okay, fine, but I can still differentiate this. I am going to denote it by y. So we're asked to differentiate this function sine x raised to tangent x. So that's our target right now for the next 5 minutes. If I have no rule of differentiating, I need to apply a mechanism such that this function goes in front as a factor. And only one function that or an operator that I apply to both sides will enable us to do that, will allow us to bring tangent in front as a factor. What mechanism, what operator would do that for us? Square root will not work. Limit, of course, will not work. Cubing both sides will not work. There's only one function that if we apply it to a power, allows us to bring the power in front as exactly. Excellent. So I apply natural log to both sides. We apply natural log to the left, and we apply natural log to the right. Okay, so then the left-hand side is natural log y, and the right-hand side is tangent x times natural log of sine x. So let's stop for a moment. Do we remember this property? Do we remember this property? Chris, no? Okay, let me talk about the property for a moment. So log has three properties. When we apply it to a product, is log x plus log y. When we apply log to a ratio, it's the same but the difference. Log x and log y. And when we apply log to a power, x raised to b, this goes in front as a factor, meaning multiplication, log x. And this is the only function, the only operator that allows a power to go in front as a factor. And that's all I wanted. I needed that tangent to come down because I didn't know how to differentiate a function raised to a function. And now, what do you think we're going to do to both sides? Differentiate, correct? Yes, we are differentiating the left and we are differentiating the right, of course, implicitly. We don't have y here. We have indirectly. We have natural log y. Okay, we just looked at the formula of natural log y prime. So what do you think we're going to write on the left-hand side? 1 over y, not enough, times,
Y prime.
right. In this case, dy over dx, because we are using implicit differentiation. And now the right-hand side, can anyone tell us anything about the right-hand side? It's not even here, I'm sorry. So the right-hand side, careful, it's a product. So you have to have a sum of two terms. Every time you differentiate a product, you have to have a sum of two terms, of two products. So the first function prime. Very good. Secant squared x times the second function, natural log, sine x, plus the first function, but times the second function prime. I'm differentiating natural log of sine x. What do I write? 1 over sine x multiplied by cosine. So here's what we have. 1 over y dy over dx equals secant squared x times natural log of sine x plus. Can anyone tell us what this equals to?
1.
Yes. How do I know it's 1? It's because it's tangent, which is sine over cosine, multiplied by cosine over sine, which is cotangent. And tangent times cotangent is 1. Okay, so I'm after this, but I have this in front. What should I do to both sides to eliminate this? Multiply both sides by? That's it. So then dy over dx equals y, but I don't want to write y. I want to write the function itself. Y was the name we gave it. So the name, sine x raised to tangent x. So sine x raised to tangent x, and now brackets, secant squared x, natural log of sine x, and plus 1. So although we had no rule for differentiating a function raised to another function, we applied log to both sides, and then we differentiated implicitly. This procedure is called logarithmic differentiation. So this procedure, this is called logarithmic differentiation. Another use of the logarithmic differentiation an hour and something ago, we looked at this. So let's do it again. I have the function g of y, which is y minus 1 to the 4th power over y squared plus 2y to the 5th. And let's say I don't want to differentiate using the quotient rule, but I want to apply natural log to both sides. Let's see what happens. So this is another application of logarithmic differentiation. So the left-hand side is natural log of the function of g of y. But what about the right-hand side? And that's one of the reasons why I reviewed the 3 properties. So can anyone tell us what to write on the right?
The y minus 1 to the 4th.
So natural log of y minus 1 to the 4th minus natural log of y squared plus 2y to the 5th. Because natural log applied to a ratio is the difference of log of the top minus log of the denominator. The left-hand side is still natural log of y, of g of y. Now, we are allowed to bring the power in front. So this is 4, natural log of y minus 1 minus 5 natural log of y squared plus 2y. This was just the preparation of the function. We only prepared the function. We applied natural log to both sides, and we came up with this expression. How do I determine g prime of y now? What should I do? What should I do? Differentiate both sides, correct? Okay, so what do we get on the left? One over g of y times
dy dx.
Yes, I'm going to write this time just g prime of y. What about the right-hand side? 4 over y minus 1 times the inner function prime, which is perfect, minus 5 over y squared plus 2y times the inner function prime, which is
2y.
plus 2. So finally, g prime of y, I have to multiply by this. And the function is g of y is the same, is the whole function. Y minus 1 to the 4th over y squared plus 2y to the 5th, and everything for y minus 1 minus 5, 2y plus 2 over y squared plus 2y. It's not fully simplified. We have to get the same answer no matter which method we apply. It's not fully simplified. Would you prefer this method versus differentiating the quotient? Not for this one. Maybe for other functions, but not for this one. I would not prefer this method. Now the other method requires you to factor, right? Factor and simplify. Here, what would you do? You still have to find the least common denominator. You still have to find the numerator and then multiply by this. Should we continue it to see that it's the same? Yes?
Yeah.
Okay, perfect. So then g prime of y, I find the least common denominator in brackets y minus 1, y squared plus 2y. This needs a y squared plus 2y, and this one needs a y minus 1. So 4 times y squared plus 4 times 2y minus, again I have the same thing. I hope you agree with me now that this is y minus 1 times y plus 1 with minus 10, right? So minus 10 y squared plus 10. And then we will simplify one of these. We have in the denominator exactly what we got before, to the 6th power. We have y minus 1, and in parentheses we still have the negative 6y squared plus 8y and plus 10. So I don't know exactly to say which one is longer or which one is shorter. I don't know. Depends on your preference. I would have used the difference quotient. Not the difference quotient. I would have used the quotient rule. Any questions here? Any questions? Do we need to look at another differentiation of a function raised to another function? Do we need another example with a function raised to another function? Yes? Okay, so let's take a look. So here are the examples. All these are functions raised to another function for which there is absolutely no rule and we have no choice but apply logarithmic differentiation.
What about when there's already a log in?
Yeah, 48.
48? Okay, sine x. Very good. Sine x raised to natural log x. So that was 48. Perfect. Was that the one?
Yes.
Okay.
What page is that on?
48 on page 223. And this is y equals sine x raised to natural log x. We have no formula for this, so then what do we do? What is our only option here?
Do another one.
Yes, apply natural log to both sides first. That's the only way. Good, so then I have natural log y equals, natural log goes in front as a factor, natural log x multiplied by natural log sine x. If you want to put the natural log first and write it in 2 steps, please do so. So we apply natural log to the left, we apply natural log to the right, and then this natural log of the power goes in front of the natural log of sine x, in front as a factor, meaning they are multiplied. It multiplies natural log of sine x. Now I can differentiate both sides. After this, I know we have about 10 more minutes. I would like to just look at applications. Why do we do all this? Why do we discuss differentiation rules? Why do we, and the whole thing. Yes. The left-hand side is 1 over y multiplied by dy over dx equals. Careful because this is a product. Whenever we differentiate a product, we have to obtain a sum of two terms. The first function prime times natural log of sine x plus natural log times the second function prime. 1 over sine times cosine x. Very good. So dy by dx, I need to multiply by y both sides, but y is sine x raised to natural log x. And then we have natural log sine x over x plus, I can change this into cosine, cotangent, of course. Natural log x, cotangent x. And this is it. Ready? Any questions? Is this okay? Do we feel better about this? Yes? No? Okay, so let's take a look at some applications here to see why we're doing all this. So here's first application, number 18. Let's read it together. The tank holds 5,000 gallons of water, which drains from the bottom of the tank in 40 minutes. Then Torricelli's law gives the volume V of water remaining in the tank after t minutes. That's the formula. That's the function. Find the rate at which water is draining from the tank after 5, 10, 20, and 40. At what time minutes? At what time is the water flowing out the fastest and the slowest, and then summarize. So we're going to copy the function. So this is problem 18 on page 234. And the volume of T equals 5,000 and 1 minus 1 over 40 T squared, I think. No, the squared is outside, sorry. Okay, and we are told the time is between 0 and 40 minutes. And the volume is in gallons. Find the rate at which water is draining from the tank after 5, 10, 20, and 40. In minutes. The rate of change of the volume with respect to time at the instant when time is 5, 10, 20, and 40. What do I have to find first? The derivative. Can anyone dictate? So let's find v prime of t. $10,000. 1 minus 1 over 40 times t times the inner function prime. So we brought 2 down, we multiplied by 5,000, we got 10,000. We subtracted 1 from the power, and now we are differentiating the inner function. What is the inner function prime? Do you all agree with the -1/40?
Mhm.
Okay, very good. So let's multiply. So this is minus. So if I divide 5,000, so that's 250, and 1 minus 1/40t. What is the measurement unit? I put t, minutes for t, but what is the measurement unit for v prime? Remember, it's a rate of change. It has two measurement units, one coming from the top and one coming from the denominator. Gallons per minute, right? Very good. So let's put this in the graphing calculator. And y equals, clear if you have anything else. So this is 5,000. I'm sorry, -250. And in parentheses, 1 minus. Yes, you can distribute if you want to. In parentheses, again, 1 divided by 40. And then x, close the parenthesis. And I will plug in with second and table. I will plug in 5, and then 10, and then 20, and then 40. Why is the rate of change negative? Because it shows direction. It's not because it's negative. It just simply shows direction. In other words, it's emptying out. So -218.8 gallons per minute, -187.50, -125, and 0. So what we conclude, and we knew that after 40 minutes, the tank is completely empty. And where is the fastest? So if I have, and we probably all done something like that, right? So maybe we punctured a bottle, right? So if I punctured this bottle of water, when do you think the rate of change, or what would be the fastest flow coming out? When would it be coming out of the bottle? When I puncture it. That would be the fastest, right? When would be the slowest? When it's empty, right? So that's what this says. It goes into 5 minutes after we open the valve to empty out the tank. The fastest would be at 5 minutes. The fastest would be at 0, right? So if we put 0 in there, it would be what? Where is the
-250.
So yes, so at 0 will be -250, and we can even put it here. That will be the fastest at time 0. And then it will decrease, right, from -218 gallons per minute to 0 after 40 minutes. Any questions here? Any questions?
How did you?
Yes?
I guess I missed how you simplified the prime to negative.
I multiplied 10,000 by -1/40.
Oh,
I
okay.
simplified a 0, and then I divided 1,000 by 4, and I got 250, and there is a minus here.
Okay. Oh, okay. Then you kept.
Better?
Gotcha. Yeah.
Okay, so I have, I know I have 4 minutes left. Let's at least look at two questions, part A and B. Let's take a look at this. That was the shortest I could find. A particle moves with position function, blah, blah, blah. At what time does the particle have a velocity of 20 meters per second? And what time is the acceleration 0? And what is the significance of this value of t? If we only get to part A, and then we'll do part B next time. Okay, so this is problem 10 on the same page, 234. Last problem. So we are given s of t, which is t to the 4th minus 4t to the 3rd minus 20t squared and plus 20t. Of course, t is greater than or equal to 0. At what time does the particle have a velocity of 20 meters per second? What do I have to find first? Yes, the velocity. Very good. V of t is s prime of t. Can anyone differentiate for us? 4t cubed minus 12t squared minus 40t and plus 20. We're asked, at what time does the particle have a velocity of 20 meters per second? So the velocity is 20, and this is 4t cubed minus 12t squared minus 40t plus 20, and I like that very much because I will factor out t, actually 4t, and I get t squared minus 3t minus 10 equals 0. So I simplified, I subtracted 20 from both sides, and I factored out 4t from this, and I got t squared, 4t from that, and I got 3t, and 4t from that, and I got 10. So obviously when one solution is not this, but one solution is 0, and two other solutions will come from here with t minus 5 and t plus 2. So t equals 5, and t equals negative 2 is not acceptable. So it appears that the particle has this velocity of 20 meters per second initially, when the whole thing starts, and also 5 seconds after the particle starts moving. And let's see if we have time for part B. We can do part B next time. It says at what time is the acceleration 0, and what is the significance of this value? We only have to differentiate and get the acceleration.